I'm going to jump into Terraform and get started with the provider block. First, I will start by specifying the AWS provider and the region I'm deploying to, in this case, US East 1, which is a common default for demo deployment due to its broad support. Next, I'm going to define a custom VPC with a /16 CIDR block. This gives us up to 65,000 IPs and plenty of room to subnet. This VPC becomes the foundation of our network, like the skeleton of the infrastructure. I then create two public subnets in different availability zones. This is essential for high availability. If one AZ goes down, the other still serves traffic. Each subnet has public IP mapping turned on, so instances launched here can access the internet. Now I'm going to create an internet gateway. This allows outbound traffic access for resources inside my VPC. Next, I'm going to attach a route table to the VPC and add a default route to the internet gateway. This route sends all traffic 0.0.0.0/0 out to the internet, which is critical for things like OS updates or serving a website publicly. These next two blocks are going to bind our public subnets to the route table we just created. Without this, traffic from the subnets wouldn't know how to reach the internet. This security group is assigned to our application load balancer. It allows inbound traffic on port 80 HTTP from anywhere and allows all outbound traffic, which is a common configuration for public-facing web services. Here's our application load balancer. It's set to span both public subnets for redundancy and uses the ALB security group we just created. This is what handles traffic distribution between instances. This is the target group that the ALB sends traffic to. It listens on port 80 and is linked to our VPC. Later, our auto-scaling group will register its EC2 instances to this group immediately. Now I set up an ALB listener on port 80. This is the actual interface that listens for incoming HTTP requests and forwards them to our target group. This launch template defines how our EC2 instances should behave when deployed. It uses the Amazon Linux 2 AMI and launches a T3.micro instance with the same ALB security group. In the user data section, I use a shell script to install Apache, start the service, and deploy a custom Fight Night landing page with an HTML message. Finally, I create an auto-scaling group tied to the two public subnets. It's configured to always maintain a minimum of 2 instances, scaling up to 4 if needed. These instances use our launch template, register with the ALB target group, and report health using ELB health checks. By writing this Terraform file, I've automated the creation of a highly available, horizontally scalable, public-facing web architecture with a full ALB, ASG, EC2 instances, networking, and security, all defined in code. This setup reflects the fundamentals of reliable cloud-native infrastructure. So now I'm going to jump into my variables I'm starting with a variable called AWS region. This allows me to define the AWS region my resources will be deployed into. By using a variable here instead of hard coding it to multiple places, I can change regions in one place and the entire config updates automatically. I set the default to US East 1, which is one of the most popular AWS regions for global reach and service availability. Next, I define a variable for the EC2 instance type. This makes my infrastructure more flexible. Right now, I'm using T3.micro because it's cost effective for demos and light workloads. But if I ever needed to scale up to a more powerful instance, I can do it just by changing this one line. Using variables like this makes my Terraform code cleaner, easier to manage, and is much more adaptable to future change. Now that we've defined and deployed our infrastructure, I want to expose a few key outputs so I can reference them easily, both from the CLI and within the AWS console. This is helpful for debugging, testing, and integrating with other tools. So first, I output the DNS name of the application load balancer. This lets me quickly grab the public endpoint where my landing page is hosted. After running Terraform apply, I can simply copy this from the CLI and test my deployment in the browser. Next, I output the VPC ID. This is useful when I want to double check the VPC in the AWS console or pass it to other Terraform modules that need to reference this VPC. Finally, I output the subnet IDs for both public subnets. This is helpful when troubleshooting or when wiring and other services that need to launch into specific subnets like RDS, Lambda functions, or even containers. By outputting these, I ensure I always have the right references ready to go without needing to look them up manually. These output make the infrastructure more transparent and easier to interact with after deployment. Welcome back to part 2 of the Fight Night infrastructure walkthrough. Since recording part 1, I've gone through and updated my Terraform files for a cleaner, more scalable deployment. I've created a new IAM profile, and I'm ready to walk you through a fresh deployment using Terraform. Test it with Locust and view performance metrics in CloudWatch. So let's go ahead and get started. So first I'm going to navigate to my Terraform folder. And I'm just going to confirm I'm in the right directory. Yes. So before applying anything, I'm going to make sure my AWS CLI is configured to my IAM user profile that I already created. Next, I'll initialize Terraform to download the necessary AWS provider and set up the working directory. Now, before deploying, I always run Terraform plan to preview what resources will be created. And this might take a little bit of time. All right. I'm just going to make this a little bigger, actually. So everything looks good. So I'll go ahead and apply the configuration, and this will deploy the full AWS stack for Fight Night. Give it a second, give it a moment to do its thing. Now that everything is deployed, I'll grab the outputs to get the ALB DNS and verify that it's live. Here's my DNS. So we're just going to visit this. Take this, copy, and there we go. That's looking good. So now our main event is live at the moment. And so now we're going to simulate real user traffic using Locust. So I'm going to use the Python module directly to avoid CLI issues. I'm just going to go ahead and just simulate the user traffic using Locust. And for number of users, we're going to go ahead and do 5,000 for ramp up, 200. I'm just going to start. So this starts a web interface at Locust, and from there I'll enter 5,000 users and a 200 user per second spawn rate, and I'm going to just start swarming. So now that we're in Locust, we can go to our charts. So let's talk briefly about what these performance charts mean. We have requests per second, measures how many HTTP requests are being sent per second. Response time tells you how fast the server is responding under load, and failures are going to show any errors like timeouts or server errors. And all these charts allow us to visualize trends in load, latency, and stability. So now we're going to go ahead and we're going to go to CloudWatch. Now we're getting a little bit of stress on the system. It's getting a little slow. And, I'm going to actually go ahead and I'm going to stop this command. Hi, so I am back now. This test caused some stress on my system, caused some of my applications to shut down. But I'm back now. I wanted to show you in real time what this looks like. So we're going to log into our AWS account. So we're able to see our application ELB dashboard. And if we come down, we can also see our CPU utilization, our status check failed, our volume, read by bytes. So the CPU utilization for the EC2 is how busy the web servers are. The request count is the ALB, the total number of requests hitting the load balancer, the target response time for latency of our app under real load, and healthy host count, how many instances are passing ALB health checks. So these charts help you prove the infrastructure can handle real-world high traffic conditions. We can also look at our EC2 instances that we created before. View dashboard. You can see our 2 instances. We can also see our VPCs along with our 2 subnets, our route tables, and our gateway. This project was inspired by the Jake Paul versus Mike Tyson fight, a real-world, high-stakes event that mirrors the scale and performance demands of live-stream entertainment like WWE, NFL games, or comedy specials. My goal was to demonstrate how I would plan for large-scale concurrency, traffic surges, and real-time availability by building and testing a highly available cloud-native infrastructure. Using Terraform, I deployed a multi-AZ auto-scaling architecture entirely through code. This showed the power of infrastructure as code, giving us version control, repeatability, and zero-touch deployment in minutes. I created an environment from scratch, a custom VPC, subnets, security groups, an application load balancer with EC2 web servers behind an auto-scaling group, and live monitoring through AWS CloudWatch. I then used Locust to simulate 5,000 concurrent users, pushing the environment under realistic fight night conditions. What I proved through this test is that I understand not only the tools, but also the principles that matter most in a live service environment. So, if hired, I bring this mindset to your team, not just executing tasks, but thinking proactively about scale, reliability, and repeatability.